In this class, we will consider energy to be conserved and mass to be conserved. Of course, Einstein showed that that's not exactly right, that you can transform some mass into energy, but that's okay. By the way, did you know that this equation is actually not complete? There's more to it. Einstein knew this. This is just not the complete form of it. Everyone writes down and thinks of E equals mc squared. It seems like all the TV shows that want to have some science component will put this equation up. It's funny that that's not quite all there is to it. There's a momentum piece apparently as well. I don't even remember exactly how it goes. It doesn't matter. In our class, we're not going to consider any systems that have any nuclear conversions going on. Even if we considered a nuclear power plant, all that's really happening in a nuclear power plant is nuclear reactions are occurring, which then generate thermal energy, which then drives a process to generate power, just like burning coal generates thermal energy and drives a process, a steam-based process, to drive turbines and produce power. So nuclear reactions are out of the scope of our class. Therefore, energy itself will be a conserved quantity and mass will be a conserved quantity. In fact, we've talked about closed systems and we've started to approach open systems a little bit. But what about open systems? Well, since mass would be conserved, then if we have 7 kilograms come into a system while 2 kilograms leave, well, that's the same thing as saying I got $7 deposited in my account and $2 withdrawn from the account. Well, obviously my account balance increased by $5. Can't tell you how much money's in my account, but I do know it increased by $5 because, well, supposedly the money in there is conserved. Now, obviously in real bank accounts they do make a little bit of interest, and you know, if there's some thievery that happens or, you know, some unethical transactions, then it's almost like money's not conserved. But, and it may seem like it's not conserved anyway as bills come along, but it's just that the outflow is so high and the inflow seems to not balance it so much of the time. But you get the idea here. We can talk about conservation of mass and conservation of energy both. And obviously if more comes in than goes out, well, then the amount of the thing increased in the system. So we need to consider mass flow rate if we're going to consider open systems. So think of just a simple piece of pipe. So we've got a cross-sectional area that's just, you know, a circle, and the flow has some average velocity. Now, in reality, you may know from a fluids class that the velocity of the flow at various points in the cross-section, you see that blue circle there. At various points in the cross-section, the velocity will be different. As a matter of fact, near the walls of the pipe, the velocity will be zero. And you probably are familiar with the velocity profile that I've got there down near the bottom of the slide in pink. You might recognize that as a laminar velocity profile. There's also plug flow or turbulent flow, but I'm not showing that here. The point is that the velocity of flow varies over the entire cross-section, but we're really not interested in that. In this class, we're going to assume that there's some average velocity, and that's what we will consider. Now, to get the total mass flow rate, well, all we've talked about so far is velocity. If we look at that little differential area, that little bitty square, that DAC, a differential amount of cross-sectional area, there's a velocity of flow through it. If we multiply that velocity of flow times that differential cross-sectional area, well, we would get a differential volumetric flow rate, right? Because we'd have, you know, length per time, that's velocity, times area, which is length squared, so that's length cubed per time. Well, that's a volume flow rate, and since it's a differential thing, well, it must be the differential volume flow through that little area. Now, if we were to then consider the fact that we want mass flow rate is just mass per time instead of volume per time. So if we just had some number that was mass per volume, well, then the volume would cancel out nicely. As a matter of fact, we have, it's called density. So the differential amount of mass flow, delta m dot, through that little bitty square is equal to the density of the fluid flowing times the velocity in that area times that small amount of area. Now, if we want the mass flow rate over the whole cross-section of flow, well, then we need to integrate. We need to add up all of those differential mass flow rates to get the total mass flow rate. That's what integration does. It just adds up things. So we would integrate the density times the velocity times the differential area across the entire cross-section, or over the whole cross-section. Now, most of the time, we don't really care about the fact that that velocity actually does change with respect to position in the cross-section. As I said before, we're going to use an average velocity instead. So what we'll do is just assume that the density and volume, or I'm sorry, the density and velocity are constants across the entire cross-section. Pull those out of the integral and just integrate the area, so we just come up with a cross-sectional area. And so the equation we'll use most of the time is that the mass flow rate is equal to density times average velocity times the cross-sectional area. Now, sometimes we don't really care about the mass flow rate. Sometimes we're interested in the volumetric flow rate itself. In that case, we don't have to multiply by density. We can simply integrate the velocity over the area, and when we do that, we'll get the volumetric flow rate. Again, we will use an average velocity, so it's easier just to write V dot equals the average velocity times the cross-sectional area. And of course, that's almost all the way to mass flow rate. So if we simply take the volumetric flow rate and multiply it by density, then we will get the mass flow rate. But since density is the inverse of specific volume, that is equivalent to taking the volumetric flow rate and dividing it by the specific volume. I've got both the equations there in boxes for you to remember and maybe write down. So we could write a mass balance just like we wrote an energy balance before, where the total mass entering the control volume during some short time minus the total mass leaving it during that time is equal to the net change of mass within that control volume during that time. So mass in minus mass out equals the change in the mass in the control volume, just like money in minus money out of your account equals the change in your account balance. But we'd like to talk about this in rate form. Sometimes we want just the mass balance to talk about the amount of mass that has entered or left, but sometimes we want to talk about the rate at which mass is entering and leaving a control volume. And so then what we do is just divide the amount of mass that enters and the amount of mass that leaves by the amount of time taken for those flows, and divide the change in mass of the control volume by that time. If we then let that time approach zero, then the first term, mn over delta t, will become the mass flow rate going into the system, and then the second term is the mass flow rate out of the system, and then the last term on the right hand side is the rate of change of mass within the control volume. If this doesn't make sense to you, think of a scheme where, I've forgotten what, I think it was Office Space, where they came up with a scheme so that how did it go? According to the movie, the amount of money that's rounded off in certain calculations would be deposited into their account automatically rather than going anywhere else. They wrote a virus and made it go, and of course things didn't go right. It's a funny movie, but I wouldn't recommend watching it with young children. There's a lot of strong language in it. But anyway, let's think about this. What if you had an account at the bank where there was a flow rate, say a penny every second flowing into your account, and there was a half penny per second flowing out of your account? Well, the net rate of flow, or the net rate of change of your account balance, would be a half a penny every second, right? You could actually get rich pretty quickly off of that, I think. Maybe you can do the math and decide. So the first term is the rate at which mass enters the control volume, the second term is the rate at which it leaves, and the last term is the rate of change of mass in the control volume. Now, when I went through college, I had to use this mass balance, and it was pretty intimidating. And it was intimidating because it was written out in kind of a very complicated way. Really, the first term in this equation talks about the time rate of change of mass in the control volume. It's like the right-hand side of the equation we had before. And really what it was doing was saying, okay, you see that integral, we're going to add up over the whole control volume, over every point within this control volume, we're going to add up the density times a differential amount of volume. And if you think about what you're doing there, you're multiplying density, which is mass per volume times volume, so you're just adding up all the mass within the control volume. So that's what that integral does. And it says, let's look at the time rate of change of mass within the control volume. And the reason they wrote it this way is because it's possible that the density could vary by some known way throughout the control volume, and you might actually need to perform this integration. Anyway, the second term really is the terms that I had On the left-hand side in the previous slide, the mass flow rate in minus the mass flow rate out, it's those two terms squished into one, and again written in a fairly complicated way, where we're saying, you know, we've got this surface, we don't know exactly what the system looks like, so we're just going to draw some arbitrary surface and talk about the velocity of flow through a differential area. That way we can have as many of these as we want across the entire surface. So you see that integral in the second term is the integral over the control surface of all of, well, what exactly is that? Well, if you look at it, the v is a velocity vector and the n is a normal to the surface. Now, for reasons I won't go into, you need to take the dot product between the velocity and the direction of the normal to the surface to actually come up with the proper mass flow rate. You basically get a velocity out of this, which when you multiply by area, well, what is velocity times area? We discovered that last time. Well, velocity times area would just be a volumetric flow rate, right? Because it'd be length cubed per time. If we then multiply that by density, well, it's just mass per time. We're back to mass per time here. And because we're integrating over the whole control surface, that dot product takes care of the fact that sometimes the normal and the velocity point in the same direction, sometimes they're opposites. In other words, sometimes mass is flowing in and sometimes it's flowing out. So this is just a really complicated way of writing something that's actually pretty simple. Why did I show you that? Well, I'm trying to convince you, I guess, that the mass balance I'm giving you is really not all that difficult. It's no more difficult than dealing with, you know, deposits and withdrawals in your bank account. Now, if we take this balance a little bit further and we define particular inlets and outlets, then the first term is still the rate of change of mass within the control volume, but now we can separate out that second integral over the control surface to a summation over whatever areas have outflow, that's the first term there, and inflow, so you see that second term. And we don't need the dot product anymore because we're assuming that they will at least be parallel, the normal and the velocity flow will be parallel, but in the case where mass is flowing in, the surface normal points in the opposite direction to the velocity vector. And so you get a negative sign from the dot product, whereas when mass is flowing out, well, then the surface normal of that control surface points in the same direction as the velocity, and so you get a positive sign. Now we can simplify this further and say, well, why bother with all the integration? If we can assume that the density within the control volume is uniform, well, then the density would just come out of the integral. We'd get the integral of volume, and we'd have density times total volume. Well, that's just the mass. So that'd be the rate of change, dm by dt, of the mass in the control volume. So that first integral term simplifies down to dmcv by dt. The second term, which has the summation over all the outlets, could also be simplified if we assume, as we did before, that the velocity of flow is uniform across whatever outlets there are. Now we still have a summation because there could be multiple leaks in the control volume, right? There could be multiple places where flow is coming out, just like there could be multiple places in the control volume where flow is coming in. And so we still need to sum over all of the outflows, but again, if the density across an entire cross-section coming out is, you know, the same, well then that comes out, as long as we can assume some average velocity, that comes out of the integral, and we just end up with a mass flow rate coming out of, you know, all the particular orifices. And the same argument holds for the incoming streams. So all we're doing really here is deriving the equation I've already given you from a mass balance that I believe your author has in the text. I wanted you to see where it reduced down to and how it's more practical to use it in this other sense. It's simpler at least. So we're really going to push the easy button. What happens when there's steady flow? Well, wait a second. We seem to be making a whole lot of assumptions. I mean, we started off with this fairly impressive looking equation that we probably didn't really want to deal with because there's so much calculus, and we keep simplifying it down easier and easier. So, wait a second. You're saying what happens when there's no change in the mass in the control volume? Well, basically, then the inflow and outflow is equal. So if we got 2 kilograms per second coming in and 3 kilograms per second coming in a different port, then for there to be no change in the mass in the control volume, the exiting flow must be 5 kilograms per second. Okay, well, we've made so many approximations and assumptions is this really worth anything anymore? Actually, it is. On average, the rate of mass flow into your car's engine equals the rate of mass flow out of it. Because think about it, there's air that comes in, fuel comes in as well, and you might say, well, yeah, but they react. They may react, but that does not change the mass. There are no nuclear reactions, only chemical reactions, and so all of that mass that comes in leaves out the tailpipe. Okay? Now, it may not leave at exactly the same rate. There may be a little bit of accumulation here and there, especially between cylinder firings, but averaged over time, the mass flow rate in equals the mass flow rate out. If the density at the inlet streams and the exiting streams are the same, which is not the case in your car, but is the case in the mixing valve for your shower, if the densities are constant, now okay, they're not exactly the same. The hot water has a little bit less density than the cold, but they're close enough. If the densities are the same, then the volumetric flow rates in and out would also sum. In other words, if you got, a gallon per minute, I don't know, I'm making it up as I go. Let's make it up this way. You got a half a gallon per minute of cold water coming in and a half a gallon per minute of hot water coming in, and they mix together, they're going to come out the shower head at a rate of 1 gallon per minute, right? Because it's half coming in, one coming out. And that's just because the mass is conserved, right? You don't create or destroy mass within the control volume. Now, a lot of times, we don't even need the summation signs, because a lot of times there are really, really useful and interesting systems that have single inlets and single exits. I know that seems strange. I know we've gone from something that was a bunch of calculus with a bunch of integrals to something that just says mass flow rate in equals mass flow rate out, but this will end up being very useful, and I wanted to show it to you. Now, you can write this in another way that's also very useful if you break it up into its parts again, so that you have the density of the flowing stream times the average velocity at that inlet times the cross-sectional area at that inlet. That will be equal then to the density leaving times the velocity, the average velocity leaving, times the cross-sectional area. Notice we're taking into account here the fact that the density could change. I mean, you could have air come into a system, like right now I've got air flowing into my indoor air handler. It's a heat exchanger essentially. The boiler's running, and so it's warming up the air. That means that the air, since the pressure is the same on either side essentially, especially once it comes out the registers, since that pressure is the same, well then the density of the air has to decrease. Its density on the hot side has to be less than what it is on the cold side. But the mass flow rate into the air handler equals the mass flow rate out of the air handler. It's not like air is accumulating within the air handler. Now, if it turns out that we've got an uncompressible flow, a flow where the density does not change, then the volumetric flow rate entering and leaving will be the same. Most of the time, the most useful equations are these last few that I've shown you. Sometimes we'll have to delve into the other ones a little bit more.